Hello. The following video presentation will introduce and explain the bomb calorimeter lab for the Department of Chemical Engineering.
Our team of 4 is comprised of our project lead, Angel Vega, Jonazart Bittner, Connor Wilson, and myself, Maddie Rahman, our procurement lead. This lab shall replace the current hydroproofing lab with concepts much more relevant to industrial chemical engineering, such as reaction productivity, runaway reaction prevention, and reactor/reactor design. The learning opportunities that arise from the implementation of the bomb calorimeter lab include greater experience with high temperatures and pressures in lab, as the calorimeter often is pressurized to over 200 psig and reaches temperatures above 300 Celsius. Other learning opportunities include industrial safety applications coupled with industrial modeling software to allow students to produce vent sizing estimates for industrial-sized processes to create safe production. The assigned deliverables for the bomb calorimeter lab design include the completed assembly and training of the ARSST bomb calorimeter, presentation of multiple feasible chemical reactions and decompositions at multiple variables with results and respective procedures for running those labs and the safety documents associated with them, as well as the pre-lab quizzes, pre-lab homeworks, and post-lab analysis documents to be implemented into the future coursework.
A bomb calorimeter is a device used to measure the heat of combustion or the heat of release of a chemical reaction by heating a substance in a sealed, high-pressure chamber and recording the results of its temperature change. For our experiment, we need to determine which reagents would be suitable for use of the bomb calorimeter. To do this, we created a decision matrix. We started by establishing a clear criteria and constraints. Our focus was on 3 main pillars: safety, cost-effectiveness, and how well the experiment fits into the existing CHI curriculum. All experiments had to meet specific safety standards. This included maintaining a reaction temperature below 500 degrees Celsius, complying with the university chemical disposal protocols, and minimizing any added risk for students or teaching assistants.
With the 2 main focuses of this lab series being chemical reaction engineering and safety, it is important that all the risks associated with these experiments have been assessed. Common chemical hazards seen throughout these reactions in the lab consist of exothermic reactions, irritants, and reactants that phase change, resulting in the production of steams and gases. To help prevent dangers in lab, an in-depth job safety analysis has been created that can be referenced and updated as labs are run. The JSA also reviews and assesses the safety, toxicology, and disposal of all chemicals and chemical productions that are being used in lab. The JSA contains emergency shutdown procedures for the ARSST as well as the chemical safety data sheets referenced throughout the document.
Our priority was to select reactions that allowed us to track theoretical compositions over time. This supports more advanced analysis of both reaction kinetics and energy changes, adding depth to the learning targets. Hydrogen peroxide stood out, scoring the highest thanks to its simple, first-order kinetics and clean byproducts. It's versatile, safe under a fume hood, and ideal for teaching reaction progression over time. Ferric sulfate also performed well. It's stable, useful for limiting reaction experiments, and ties into real-world wastewater treatment applications. Based on our findings, hydrogen peroxide and ferric sulfate were selected for procedure development, with esterification kept as a strong backup option. However, due to supply chain issues and ferric sulfate's reagents being backordered, we had to pivot. Our third option, esterification of methanol and acetic anhydride, became the fallback since those reagents were already in stock. So we moved forward with hydrogen peroxide and esterification procedures, with both reactions supporting curriculum goals and safe lab practices.
Welcome to the procedural video for the ARSST bomb calorimeter by Faust. We will begin by clicking on the ARSST shortcut located in the computer, where then we can put in our sample materials description. We can then proceed to setup, select the right polynomial, and ARSST mode, and continue to the test screen. Now we are ready to set up the test cell. We will set up the test cell inside the installation and then place it inside the sheath. After being placed inside the sheath, we will add in the magnetic stir bar and then place the entire sheath inside of the vessel. From there, we can plug in our heater cords coming out of the sheath and then our thermocouple before we close the lid. After making sure everything is thoroughly lubricated with vacuum grease, we can begin by putting on the top. When putting on the top, we make sure that the feed port enters the test cell itself. After that is finished, we can then put on the ring to secure a seal. We can then screw on the pressure lines using 2 wrenches. From this point, we can plug in all of the cords from the bomb calorimeter to the computer, and there will be 3 plugs total, one for the heater, one for the thermocouple, and one for the pressure gauge. Before pressurizing, we always make sure that the rupture disc faces the back of the fume hood. We can then use the regulators on their nitrogen tank to begin to pressurize our system above what we believe it to be. If there is no hissing, no pressure drops, and we are positive that there's no leaks coming from the vessel, we are okay to depressurize and begin creating our sample. We do this by first pouring our reagent into a weigh boat on top of a scale, and then using a syringe to pull out as much as needed for the experiment that we are running. The syringe then screws onto the top of the ARSST, where you pull in 1 milliliter of air from the system, and then you push the rest through. After the reagent is in, you close the feed port line, then you are able to repressurize the system, flip the 2 switches on the computer, and you are able to click run on your experiment. For more information, see the bomb calorimeter lab design procedural document.
After each ARSST experimental run, data for time, temperature, pressure, and ear power is exported to Excel. This data is then processed using a MATLAB script developed by our team, which generates key plots that applies curve-fitting models. These MATLAB graphs are then used, coupled with initial data such as test mass, composition, and chemical characteristics, to determine values such as B, the ratio of total heat capacity of the bomb calorimeter system, the adiabatic temperature rise, the external change in temperature, the chemical specific heat capacities, and more to produce values defining enthalpy, rate of reaction, and concentration as a function of time. These results help us understand how changes in reactant ratio, pressure, or heat rate affects the thermodynamics and reaction performance of the system. Beyond the reaction data, we've also performed safety-based calculations about vent sizing and scaling up the process for industrial use. These ensure that the system can relieve pressure safely in the event of a runaway reaction. These calculations can be done by hand or through the first software available for use in the Berge computer lab. Our team has documented both approaches with step-by-step examples. These calculations can be included in the future post-lab analysis exercises.
The final deliverables for this design project are the educational documents to be implemented into the Chi 401A lab coursework. These documents include a pre-lab quiz and a pre-lab homework with both conceptual and calculation problems, both of which are accompanied by answer keys and variations depending upon the reactions being run. The final student document included is a post-lab analysis report that, along with other assignments, focuses on in-lab and industrial safety, along with chemical reaction and engineering fundamentals. We have a few key recommendations to improve the safety, efficiency, and educational value of this experiment within the Chi Lab curriculum. First, we recommend replacing the current glass reaction cells with stainless steel cells. While glass is translucent and allows for easier cleaning, it's fragile and prone to breaking. Second, we suggest exploring faster, safer reactions such as production of iron sulfate. Using properly concentrated reagents, reactions like these can still yield meaningful thermal data while reducing hazards and simplifying waste disposal. Lastly, we recommend adding a supplemental in-lab activity to run alongside the main experiment. The additional activities could reinforce reaction theory, data analysis, or even give students a hands-on role in setup and calibration. These improvements aim to make the lab more engaging, more efficient, and more aligned with the real-world chemical engineering practices.
We believe that this lab series also effectively demonstrates and promotes safe lab behavior and education into future industrial safety applications. Thank you for watching this presentation, and bear down.